So we continue with our approximation results concerning the Lebesgue measure. So we have the following proposition. Let E contained in Rn be a measurable set. That means, as I always say, Lebesgue measurable set of finite measure. Given epsilon greater than 0, there exists a compact set K contained in E such that Mn of E minus K is less than epsilon. So you can approximate it. We saw, given any set, we can approximate it from the inside by means of a closed set. Now you want to approximate it from the inside by a compact set. Here we need the finite measure for the same result, that the difference is less than epsilon, because if E is of infinite measure, compact sets are always of finite measure, and therefore you cannot expect that result. Okay, so proof. We will do it in a few steps. So step 1. Let eta be greater than 0. Then there exists V open, V containing E, and Mn of V minus E less than eta. This we already saw. Given any measurable set, it's one of the criteria for measurability. So okay. So let B0R, this is a notation I will use in future also, equals open ball, center 0, radius R, and B bar 0R equals closed ball, center 0 and radius R. Okay. So n a positive integer, okay, and you write Vn equals B0n intersection V. Then Vn are all open. Vn increases to V. So V has finite measure. Why? V has finite measure because E has finite measure and V minus E is less than eta. So measure of V will be less than measure of E plus eta. So V also has finite measure, and therefore, and you have that limit Mn of V, Vn as n tends to infinity equals Mn of V, because you have an increasing sequence, and therefore there exists M such that Mn of V minus Vm can be made less than eta. Then E minus Vm is contained in V minus Vm, and so this implies that measure of E minus Vm is less than eta, and now Vm no longer, it may not contain E anymore because we have taken the intersection with B0n and then we are taking the limit, but Vm is a bounded open set. Step 2. So there exists a closed set F contained in Vm such that Mn of Vm minus F is less than eta. Okay. So now F is bounded and closed, since Vm is bounded, and so this implies F is compact. Step 3. Thus, by steps 1 and 2, given epsilon positive, there exists a bounded open set W such that Mn of E minus W is less than epsilon by 3, and there exists a compact set K1 contained in W such that Mn of W minus K1 is less than epsilon by 3. Finally, there exists F1 closed, F1 contained in E such that Mn of E minus F1 is also less than epsilon by 3. Set K equals K1 intersecting F1, and therefore K, so this implies F1 is, K1 is compact, F1 is closed, so this means K is compact, and F1 is contained in E and K is contained in E. So now E minus K is nothing but E minus W union E intersection W minus F1 union E intersection W intersection F1, but that is nothing but W intersection F1, because E intersection F1 is F1. So this W intersection F1 minus K1. And that is contained in E minus W union E intersection W minus F1 is contained in E minus F1, and that is contained in W minus K1, the third one. Okay, and therefore Mn of E minus K is less than or equal to, measure of E minus W is less than epsilon by 3, E minus F1 is also less than epsilon by 3, and W minus K1 is also less than epsilon by 3, and that's equal to epsilon. So the only thing you really have to check here is this particular set theoretic identity. So let me draw a picture for you so that, so you have here the set E, and then what did you do? You found a bounded open set W which was like this, and then you took K1 which is a compact set and a closed set, and you took a set F1 here. So F1 intersection K, so this is the compact set K which you finally got, and this is the set E here, and therefore if you want E minus K, it consists of actually three parts, which is E minus W, which is here, Okay, and then you have that E intersection W minus F1. Then W intersection F1, which is here, minus K1. So if you add all that, that's precisely E minus K. Okay, so all these shaded new things which will give you E minus K. So that you can check it yourself, and then so this proves that approximation property. So remark. So you have E contained in Rn measurable. Then on one hand you have Mn of E is equal to infimum Mn of U, E contained in U, U open. So this means the open sets determine the measure of any set, open sets which contain E. So this is called outer regular. Then if Mn of E is finite, then you have Mn of E is nothing but sup of Mn of K, K contained in E, K compact, because of the previous proposition. It's always bigger than or equal to the supremum, because Mn of K is always less than or equal to Mn of E, but we found you can find a K which is very close to Mn of E, and therefore it is precisely the supremum. In fact, the supremum relation you can also prove without this restriction on Mn greater than less than plus infinity. I leave it as an exercise for you, and therefore this is called inner regular. So, any Borel measure, that means a measure defined on all Borel sets, so Lebesgue measure is an example, which is both inner and outer regular, is called regular. It's also or a radon measure. A radon measure is a Borel measure which is both inner and outer regular. So this is just a definition. Okay. Now we move to approximation of functions involving measurable sets. So definition. So we have X, any set A contained in X, then we know what is chi A of X equal to 1 if X belongs to A and 0 if X does not belong to A. Okay. The definition again. Omega contained in Rn, an open set. A step function defined on omega, we've already done it in one dimension, is a function of the form f equals sigma I equals 1 to small n aj chi of ij where aj 1 less than equal to j less than equal to n are constants and ij 1 less than equal to j less than equal to k are boxes contained in omega. So it's a function which is made up of boxes, characteristic functions of boxes. Okay, so now a very simple proposition. I in Rn, a box, so it could be open, closed, half open, whatever. Epsilon greater than 0 given. Then there exists phi belongs to Cc of Rn, that means continuous function with compact support in Rn, okay, and such that 0 less than equal to phi less than equal to 1 and measure of set of all x in Rn such that phi x is not equal to chi of I x this measure is less than epsilon. Further, support of phi will be contained in I. Okay, so let us see what this means. So you are given a box and you are given the characteristic function of that box. Then this characteristic function is what? It's a discontinuous function. It's 1 in the box and 0 outside. I am saying that I can find a continuous function with compact support which is equal to this except on a set of very small measure, and that I can dictate how small I want. I can dictate, and also I can ensure that the support will be also inside I, because outside I anyway characteristic function is 0, so this function phi is also 0 there. So we want to know how to do this. So proof. So we can find boxes J1, J2 such that J1 is contained in J2 is contained in J2 closure which is contained in I. I is a box, so you can make smaller boxes by shifting the boundaries as I already said. Okay, and such that Mn of I minus J1 is less than epsilon. So in 2 dimension, let me draw a picture here. So this is a box I, and then I make smaller boxes. J1, J2 and then I. Okay, and then I make these boundaries sufficiently close so that they are all the whole thing difference in the area is less than epsilon. So that I can do. Now you use by Urysohn's lemma there exists a continuous function phi from continuous function on Rn such that 0 is less than equal to phi x less than equal to 1 for all x. That is true. Phi is identically 1 on J1 and phi is identically 0 on J2 J2 bar complement. So you have two disjoint open sets. So J1 is open box. Oh, let me write that first. J1 open box. Okay, so I have two disjoint open. So J1 should be a closed box, because we are going to apply Urysohn's lemma, and so let us do it correctly. So J1 is closed box, J2 is open box. Okay, so this is J2 complement. So you have J2 complement is a closed set, J1 is a closed set, and J1 intersection J2 complement is empty, and J1 J2 complement are closed. Therefore, by Urysohn's lemma, I can construct such a function which is like this. Okay. So this implies that support of phi, it is 0 outside J2 complement. So this is contained in J2 closure, which is contained in I, and J2 closure is compact. So this implies that phi belongs to CC of Rn, and support of phi is contained in I. Now what about the set of all x such that phi x is not equal to chi I of x? This is in fact contained in I minus J1, if at all, because on J1 both the characteristic function of I and the function phi both are equal to 1, so they are equal there. So and then Mn of I minus J1 is less than epsilon. So that proves the theorem. So it's just a simple application of Urysohn's lemma. Okay. So now we can use this to form the following corollary. Omega in Rn, open set, and f from omega to R, a step function. Epsilon greater than 0 is given. Then there exists a phi in Cc of omega, continuous functions with compact support contained in omega, such that Mn of set of all x in omega such that fx not equal to phi fx, this is less than epsilon, and in addition, and max mod phi fx x in omega is less than or equal to max mod fx x in omega. I've used max here over the open set, but then we are dealing with a step function, so it has only a finite number of values, so it will definitely attain its maximum. Okay, so proof. So let us take f equal to sigma I equals 1 to k alpha j chi of ij, and without loss of generality, ij's are all disjoint. So there exists functions phi j by the preceding proposition in Cc of Rn such that 0 less than equal to phi j less than equal to 1. Support of phi j is contained in ij, and the measure of the set of all x in Rn such that phi jx not equal to chi jx is less than any small quantity. I am going to take epsilon by k. Now define phi equals sigma j equals 1 to k alpha j phi j. So set of all x in omega such that phi x is not equal to fx is contained in union j equals 1 to k. Set of all x in omega phi jx not equal to chi jx, chi ijx. Because on the complement of this, phi jx will be equal to chi jx for all j, and therefore phi will be the same as f. Okay, so everything will be okay. So this is contained in union j equals 1 to k set of all x in Rn such that phi jx not equal to chi of ijx, and therefore so this implies now each of this is measured less than epsilon by k. There are k of them, and therefore mn of set of all x in omega such that phi x is not equal to fx is less than epsilon. So we have found a continuous function phi with these properties. And now support is contained in ij, all disjoint. So this means that the max of mod phi x in omega is less than or equal to max mod alpha j 1 less than or equal to j less than or equal to k, and that's equal to max of mod fx, because all the phi j's are less than or equal to 1, remember, and they are all on disjoint supported sets, and therefore this is equal to max fx x in omega. So that has the other property. Finally, phi has compact support because support of phi j is in ij. Ij is a finite box, so inside you have a closed set, which so it's closed bounded, therefore it's compact, and compact support contained in union ij j equals 1 to k, and that is of course contained in omega, and therefore phi belongs to cc of omega. So that completes the proof of this theorem. Okay, so we will continue afterwards.